welcome to your first video for this course. This is all about an introduction to chemistry. At the end of this video, you should be able to answer the question, what is chemistry exactly, and what does it really mean to be a scientist in this field? Okay, so let's get started. Before we even tackle what chemistry is, we first have to talk about what science is, okay? What science is. Right, and our working definition here is that science is the study of our natural world, okay? And there's a lot of different branches of that science. For example, we could have biology or geology. Let me get my pen all situated here. Let me probably start over this video because I can't even do this. Take two, here we go. All right, welcome to your first video in this course series. This is all about chemistry, So at the end of this video, you should be able to answer the question, what is chemistry? What is chemistry? And before we even tackle that question, we first have to zoom out and think about, well, what is science even? Okay. And our working definition of science is that it's the study of our natural world, and we could have a number of different things. You can study biology, that's a science discipline. You could be a physicist, study the movement of particles through our universe. Maybe an astronomer, when you study the stars in the solar system. Maybe you're a geologist, studying rocks and earth, the study of our earth, or maybe an oceanographist, right? Science is all-encompassing, and it's divided into several disciplines, and chemistry is one of those disciplines, okay? Chemistry is just one of those disciplines, and we define chemistry as the study of matter and all the changes it undergoes, okay? Matter's all the changes, the study of matter and all the changes that it undergoes. So obviously, we're going to study matter, we should probably know what matter is. Okay? And matter is going to be described as anything that has mass and takes up space. Anything that has mass and takes up space. Okay. Perhaps you're thinking to yourself, oh, I've heard those words before. But essentially, matter is the stuff that makes up the universe. The stuff that makes up the universe. And sometimes we think about matter as being tiny, tiny particles, okay? So even, the pencil in your hand, the keyboard under your fingers, that is all made of matter. Even the air floating around your head. Okay? All of that is made of matter because it has mass and it takes up some space. Therefore, it's got to be made of matter. Okay. Before I even move on, I want to make one distinction, and this is the distinction between mass and weight. Okay. So they are both similar. They're both similar values, except that mass is one of the properties of matter, and that's going to be the actual measurement that affects the actual amount of matter. Okay, so this is a quantitative number of particles. Okay, the number of particles. So maybe you yourself, you're made of a certain number of particles, call it X. All right, you're always made up of that many particles. No matter where you are in our universe, you're always made up of X particles. Your weight, however, is the measure of the gravitational pull that Earth has on that mass, right? On your number of particles. So depending on where you are in time and space, different different bodies have a gravitational force exerted on you, or exert that force on you, always that same number of X particles. Okay, and so your weight could change based on where you are in the universe, but the mass, the number of particles you actually are, will never change. That's why when you jump on a scale here on Earth, you might weigh a different amount than what you would weigh on the moon or a smaller planet. All right, and all science is kind of done using this, what we call the scientific method. And that's just an approach to scientific study, okay? And it's systematic, meaning that it's always happening As soon as you finish one step, that leads to another, which leads to another, which leads back to the beginning. So science is kind of always happening. And you've honestly been doing this first part of science probably your entire life, and that is observation. Okay, and we make observations using our five senses. That's, our smell, our sight. We feel, hear, and taste. So when we observe, we just use our five senses, and we develop a testable question when we do that. Okay? And I like to define a testable question as any question you can answer without just simply Googling it. Okay, so it's not 5 times 5. What does 5 times 5 equal? That's not really a testable question using this scientific method. Once we have a testable question, though, we generally try to make our best judgment of what you think might happen. Okay, and that guess is referred to as a hypothesis. Okay, so a hypothesis is just a guess. It could be right, it could be wrong. We don't know yet. But we test to see if we are right or if we are wrong by performing an experiment. Okay? And that experiment is going to be just a set of controlled, repeatable trials that test our hypothesis. Okay, so we're testing to see if our educated guess was right or was wrong, and we do that by collecting data. We collect data, and there's two types of data. We can have quantitative, which is anything to do with numbers, or we can have qualitative, which is any kind of observation. Qualitative data might be the color something turns, or maybe the size of a material, how it feels. So all of these are usually going to be observations. So after we collect our data, we then draw a conclusion. We look at our data, find a pattern, and then we answer our question and determine whether our hypothesis was right or wrong. Right or wrong. And, there is no good or bad. It's not a bad thing for a hypothesis to be proven wrong. Okay, that's eliminating one possibility, which is a step in the right direction. Okay, and once we make that conclusion, these supported hypotheses can go into a wider theory of how the natural world works. Okay, so a theory is going to be supported by many experiments, right? So a theory is very wide-ranging. It could be the product of many, many experiments. And further than that is a scientific law. And these are always going to be natural laws that the world exhibits that we have yet to be able to disprove. Okay, that doesn't mean we cannot disprove them, but as of now, our collective knowledge currently, scientific law is something that has not been disproven. Okay? The law of gravity, for example, has never been disproven. So we therefore take it to be a law, meaning that every body has to follow it. All right. Those are the 6 points of our scientific method. Okay? Let's focus on our experiment. Okay? So this is, again, to test a hypothesis. We design an experiment, testing a hypothesis to form a conclusion, okay? That's the purpose of our experiment, is to form a conclusion and test to see if our hypothesis, our best guess to a question, is correct or not. Okay? So experiments, have a few parts to it. All good experiments have a good title, which we always use this kind of framework, the effect of the independent variable on the dependent variable. And we'll understand what that might mean here a little bit more in a second. And your hypothesis is always going to be in this if-then format. If-then format. And remember, this is your best guess for the answer to a question. That's your best guess. If this happens, then I think this will happen. Okay. If it is sunny outside, then I think I will wear a t-shirt. One of the variables in our experiment is called the independent variable. This is arguably the most important because this is the one that you change. You change the independent variable. Sometimes I like to say I change the independent variable, the IV, okay? I change the IV. And in any good experiment, any proper experiment, we should only ever change one variable. Everything else should remain the same, okay? And that one variable you change, you should change it in more than one level. More than one level. So what that means is that you should not just change it one specific way. You should change one thing multiple ways. Okay, and that will give you a determination of which one is the best way. All right, and you should do that always at least 3 times. Okay, you have to be able to repeat the number of times you do an experiment, and this is just to be certain that your first trial was not an anomaly. It wasn't out of mistake, okay? If you do something 3 times, that signals that, okay, your data is actually valid. It is true that if this happens, then this happens. Moving on, there are 3 more portions of our experimental design. The second is a dependent variable. Okay, so now remember we have an independent variable, which is the variable that you change. I change the IV. The dependent variable is the variable that responds to that change, or the variable that you measure. Okay, you measure that dependent variable. Okay. A control is similar to our independent variable. However, this is one that is going to be considered like the standard of comparison. Often this is 0. Often this is like a baseline value. Base value, okay? So you may totally omit what you change in one trial to see if, similar to giving a placebo in a vaccine trial, for example. So not all experiments have this control. This is kind of a case-by-case basis. Finally, all of the other variables in your experiment should remain the same, and we refer to as all of those as being our constants, okay? So we can only change one variable, we only measure one variable, and all the other variables in an experiment are what we call constants. Okay, so those are our parts of the experimental design, which goes into what it means to kind of be a scientist and how scientists perform. As scientists collect data, we sometimes do so in very precise ways, right? And when we measure things precisely, we also must know how to communicate them precisely, right? And one of the techniques we use to communicate large and small numbers is called scientific notation. We use scientific notation for large and small numbers. Okay? There we go. Used to express very large or very small numbers. The first number in any scientific notation must be between 1 and 9, and I'm going to add to that it's never, or it's only one number to the left of the decimal point. Okay, we'll see some examples of what that looks like in just one moment. The main reason why scientists use scientific notation is to be able to communicate our values effectively. Okay, so often, if we have a very small or very large number, it's hard for our brains to kind of comprehend how small or how large. Okay? And scientific notation allows us to do so. And this is a simple trick where I say that the exponent tells you how many times you should move the decimal point over. Okay, so we'll see what that looks like here in 1 second. And finally, if a number is larger than 1, the exponent is positive. If the number is smaller than 1, the exponent in a scientific notation is going to be negative. So for scientific notation, we're always going to follow the form x point y z times 10 to the exponent here. That's going to be our exponent. Okay? notice that this number is always going to be only 1, okay, and that's always going to be 1 through 9. The y and the z can change. This can change. And if this exponent is if this exponent is positive, that means its number is going to be larger than 1. If it's negative, that means that number is going to be smaller than 1. So let's do a few examples here. How can I change this very small number and put it into something more digestible, more easily communicated in scientific notation? So remember, we want this form x, y, z. And we want to get there by putting that decimal point there. So we want 5.24 times 10 to the, that little caret is the exponent, so I'm writing in superscript. And the question is, what is our exponent going to be? We determine that by seeing how many times we've had to move our decimal to get it to its desired location. So let's count 1, 2, 3, 4, 5, 6, 7 times. Okay, and our exponent becomes -7. 5.24 to the -7. And look, our exponent is negative. That must mean we have a number smaller than 1, which is indeed the case. Our number here was 0.000000524. That's just one example. Let's do a few more examples here. So remember, we want in this form x decimal yz times 10 to the some exponent. Okay. In order to get into that form, we move our decimal point 3.48 times 10, and the number, we move it over 1, 2, 3. This number is smaller than 3, so it's going to be a negative exponent. And our second number, 1.90 times 10, 1, 2, 3, 4, 5, 6. And there you go. A little bit clearer values for you. And let's try to go the other way. Can we go from scientific notation to standard notation? So now we're going to take our exponent and we're going to move our decimal point that many times. In this case, 1, 2, 3. So we should have this is equal to 1290. And this one, now we're going to move to the left since it's a negative exponent. 1, 2, 3, 4, 5. And we put zeros as placeholders if there are no more non-zero digits. So our number becomes 0.0000450. I'll erase. So you should be able to go from standard to scientific notation and